Um, well, last time we talked about introducing fluid flow and pressure diffusion, and so what I wanted to talk about today was just to recap what we talked about in terms of that last time, and then take it the next step, because we said last time that when we are able, we'd like to be able to develop the governing equations from a very intuitive and physically based approach. And that doesn't tend to be possible when we start talking about two-dimensional and beyond problems. We did it very simplistic, straightforward last time to introduce, just using Darcy's law, we developed the conductance matrix. You recall that last time we developed this conductance matrix K, and this allowed us to link flow rates to nodal values of heads through this K matrix. And this K matrix was actually, for the case that we were dealing with, just given by hydraulic conductivity, an area divided by a length of the element, and then this template, which is 1 minus 1 minus 1, 1. And this is perfectly fine for this template of an element that we had that happened to be a prismatic element, one-dimensional only, because it had flow only along the length of it. It was defined in terms of nodes 1 and 2. And in terms of these parameters which make up this was the cross-sectional area of the face, and it had a hydraulic conductivity K, and it had a coordinate system attached to it which gave us, defined the length of the element. And that length of the element was just L. So this defines all the properties that are present here, and we would define either a head or a flux at node 1, or a head or a flux at node 2. And so that defines all of the components that would exist inside this. This was just the nodal heads, H1 and H2. And likewise, this was the nodal fluxes. So that was very straightforward, because we were able to derive it absolutely directly from Darcy's law. And we could do that by this trick, by saying that these fluxes out of the element, instead of being velocities, which would have both direction and magnitude, were really just defined as to whether they were in or out, flowing into or out of the element, in which case they'd be positive or negative. But it turns out that we can't really get away with that when we start talking about two-dimensional problems. And so what we'll do today is we will try and work with the governing equations which come from conservation of mass in what's referred to as the Galerkin Formulation, which is good for both one-dimensional problems, which we've done, but also two- and three-dimensional problems. And then we'll try applying that to a one-dimensional case, just to be able to make sure that we still get the same results we did last time. So that's our task for today. And I think we'll probably have time. With this one-dimensional element, we'll look at some numerical solutions to be able to solve exactly the same problem that we dealt with last time. So that's our plan for today. And so I'll skip this because we've done this already. But when we're talking about 2D problems, in which this is the case, often in mechanics we end up with this kidney-shaped surface, which defines our domain, if you like. The problem that we want to solve, we know that the governing equation for this, because we talked about it last time, is something like hydraulic conductivity in the x direction times the second order partial with respect to h in the x direction, kx d2h dx squared, plus a portion that's in the y direction. The hydraulic conductivity measured in the y direction, again by the second order partial differential, partial derivative of that, d2h dy squared, and we're going to put this equal to some term which is a capacitance term, which is how head changes as a function of time multiplied through by something, some parameter. And this parameter here, I'm not sure we've defined it already, but it's specific storage. It's thinking for some reason. Don't know. And it's just a measure of how much capacitance the system has. So you change the head by 1 meter, you get a certain amount of fluid out of the system, not by dewatering the column, but by the fact that you're changing the pressure in the column and it's expanding or contracting. So we won't go into details in that. You certainly pick that up in a hydrology class. But just take it as that this is the equation that we're trying to solve, and this might be referred to as a groundwater flow equation. And so this governing equation, which we've written here, is true everywhere within this domain, which has some area A. And on the boundary of this, I guess we could also have a flux. And so this is this here. So if you push water into the system externally as a source or a sink, one being the negative, the other one, then this has an extra term. So this would be rainfall, for instance, if this was a plan view of an aquifer, for instance. And so what we can do is we can define two boundary conditions. And so we didn't really implicitly say that, but if we skip back to this, remember that we said within the boundary conditions at the nodes of this element, we could either define what the heads were, which was the conditions that we had for our dam problem. Upstream head was 25 meters, downstream head was 20. And so heads were defined at both ends. Or we could define the flow rates through the system alternatively. We couldn't define both at one point, but we could define one or the other. And so the same is true if we look at this geometry here. So instead of being this one-dimensional problem where we have just the ends of this brick defined as our boundaries, now our boundary, because it's a two-dimensional problem in terms of x and y, our boundaries are actually, the area of our domain is two-dimensional, has length meters squared, and the boundary is one order of magnitude, one order less than that, right? So a two-dimensional area has a line, which is the contour, which defines the boundary. And on this boundary, we could define two things. We could define a portion which we'll call S sub A, where we define the head, one of our two complementary boundary conditions. And on the rest of the boundary, just as an idealization, we have the converse, and we define a flux. So the flux is defined on S sub B, I guess, and head is defined on the rest, hydraulic head. And so the other thing that we can also define related to this is that if we know, for instance, what the magnitudes of the local heads are just inside this contour, then from Darcy's law, we know that Qx, for instance, at this point, so in other words, we take this portion of the contour and we divide off this little triangular element that encases that. And if we look at Qx that's going into this, then we can just get that from Darcy's law as minus hydraulic conductivity in the x direction times the gradient of head in the x direction. So this is just Darcy's law. And so we know that the flow, if we knew exactly what the head gradient was at this point, we could calculate what the flow across this surface was here. We could do the same for Qy, because that would just be the complementary value. It's just be the same as writing this expression for Qy. This radiator is really annoying me, but apart from that, just by permutations of the x's and y's. And so if we know what the individual gradients are at these individual points, we could figure out exactly how much flows into this element. Because it's steady state, we know that the amount that flows in through x and y faces has to be flowing out across this contour. We can write this condition here. And the condition is that the flux that goes across this is equal to the flow rate that goes in to the face Qx, the flow rate that goes in to the face Qy, and multiplied through by this direction cosine, which conditions the orientations of the flux vectors, if these are unit length, to be able to give us the total amount that comes across this face. And so this is just a way of being able to express the local flows in the x and y direction in terms of a single magnitude that comes out of here. And the reason for doing that is a little bit similar to this, one-dimensional element, is that we made this simplification that no longer we're treating Darcy's law as a vectoral quantity. We want, instead of being able to define a flow velocity with both direction and magnitude, as one that has only magnitude and is either positive or negative, whether it's in or out. And this allows us to do this. It allows us to take two fluxes and combine them together into one, which is the maximum flux across this boundary, and is given by the sum of these two things. So that's the reason for defining this. So take that on trust. And so what we'll do is we'll try and take this partial differential equation and convert it into something that we can write a very simple statement for. And I'll give you the punchline already. The statement is going to equal something like this, as you might imagine. And most importantly, this conductance matrix is going to look something as we talked about before but really didn't explain, and that is this integral of some matrix yet to be defined, A transpose d A over the area in this particular case. Don't need to worry what these terms are, all will become clear. But the end goal of this is to be able to have a set method through this to be able to make this so that when we want to be able to compose our system of linear equations, ax equals b, which is really what this is, then we can do that. So what our attempt to do is to take this partial differential equation, which is continuous within this area, and make it into a discrete equation, which for this geometry, we'd like to know exactly what this equation was that would allow us to represent an individual element, which would be a small part of this overall domain. Because we'd like to take this element out and be able to draw it and figure out exactly what the nodal connections were for that. So that's where we're going. And we've made the point that we have to be able to do that by taking this continuous relationship and making it discrete. And of course that's the benefit of FEM, is it allows you to be able to work with these discrete components, which are therefore just algebraic, nothing more than that. So this, I think, is a little involved. So I think what you should do, if you like this stuff, PDEs and manipulation, great. if you don't, sit back and try and get hold of the big picture. We'll do things in two ways. We'll do it with a trip through this little derivation here, which probably runs a few pages. And then there's a one-page portion which really summarizes that. So that's our goal. So look at this in terms of the big pictures, and I'll try and explain it in broad terms. To me, the only important part is the end result, and the end result is this. And the reason I say that is because we made this point last time, is that for all PDEs that look like this, this will be the equation. It will always look like this. And so you don't have to rederive this. You just know that if you have an equation that looks like this, then by de facto, the expression that takes it from a PDE to an algebraic term is just that term. So here's the big picture look at this. This is our governing equation that we've talked about. This term is flow in minus flow out. That's all it is a mass balance between fluids going in and out. Equals rate of accumulation. Yeah, you can get it in. So that's it. And I suppose the Q term would also be in addition to accumulation, right? If you're pouring rainfall into the system, it's accumulating. So whatever doesn't, if the inflow rate doesn't equal the outflow rate, then there is some accumulation. And that's physically what these terms represent. Refer to this as a capacitance term, and this is a steady state term. We said that we can define our boundary in two parts. They have to be unique. So there's a part on which the head is prescribed, which we call S sub A. You remember from before? And a part on which we prescribe a flux. They don't have to be continuous, so it could be head flux, head flux, head flux around the boundary. Absolutely open to us to do it, but it's just easy for us to divide it into those two lumped categories. And if it's the head is prescribed, then we prescribe a head on that boundary. We know what that is as a boundary condition. And if the flux is prescribed, we know what that flux is on the boundary. And if that flux is prescribed, then we know that if we're sucking fluid out of this, then by definition, if we are sucking it out of this particular part at some flow rate here, the gradients that have to get set up to accommodate that have to be these magnitudes that are here. And so this is saying that if we suck fluid out of the boundary, then as a consequence of sucking it out at this rate, the gradients that have to get set up are going to be this in the x direction and this in the y direction, because we have this little triangle that they're flowing into. That's all those things are saying. So what we could do is we could say that we could take this governing equation, this equation 1, and we know this is going to be true. It's going to be true every single point within our domain. And so what we could do is we could write out equation 1, which is right here. Whoops, this is equation 1 right here. Not doing very well. This is number 1 here, where we've set it equal to 0, just by taking this onto the left-hand side. So if we do that, then this is equal to 0. What we could also do is we could take this boundary condition, which is present only on the boundary. So this one here, this condition we've just defined here, is present only in the interior of our domain. And we know that that's equal to 0, which is this term here. If it's equal to 0 at that point, we could also add to it this condition, where we do exactly the same as before. We make this into equation 3 into an equation that equals 0 just by taking QP onto the right-hand side, I guess, in this case. And then it equals 0. And that's this term here. So this is definitely true at every point within a domain. This is definitely true at every point on the boundary, that they're equal to 0. If they're equal to 0, then we could multiply them by some number, and they'd still equal 0 at any individual point. And we could also sum all these zeros up through everywhere throughout the body as well, and they still equal 0. And so we haven't really done anything to violate anything. We've just added two equations together that have to equal 0 at every point. We've multiplied them by a number that we haven't said anything about yet, and they should still equal 0. And we've integrated them. So in other words, we've taken them at every single point and we've summed up the number together, and they should still equal 0, which is really the definition of an integral. Because the bounding equation only exists within the area of our kidney, then the integral can be anywhere within that kidney. And because the boundary condition for flux on the boundary is only true on the boundary, then the integration, the summation we should do on that, it only exists on the boundary, so we can only sum it on the boundary. But basically what we've done is nothing, we haven't violated anything yet. We've just seen that these two equations are equal to 0 everywhere, and we've summed them up and they should still equal 0. So in this, we have a second order PDE. And what we might want to do is change that so that instead of dealing with this second order PDE, which is a bit clumsy to deal with, we can deal with a first order PDE. And so to do that, we use a standard result, which is Green's identity. So if we take this first expression here, I'm already spending more time doing this than I really wanted to, but never mind, which is this here. And we can write that as a standard result. We can write it out as two parts. So instead of a second order PDE, which is these two parts here, which give us the d2h dx squared term, we can write it in terms of a first order term, but multiplied by rate of change of this weighting factor here. This arbitrary number is going to be between 1 and 0 that we use, and we convert it to this, which is done over the area of the elements. And a second part, which is just a first order expression, which actually looks a bit like Darcy's law, k dh dx, multiplied by a normal to the boundary vector, which is jumped in here, just a standard result, which together define this. So in other words, what we're doing is we're taking, can't keep them both on the same page, we're taking this part here, and instead of writing it as a single expression, we're writing it as two expressions, which we can substitute back in. And then we'll permute this to the second one, and we'll do exactly the same. So these two second order terms we'll get rid of. And so if we do that, then keep on the same page. So the first term, if I draw a circle around it, this term is the first one that comes out of this, which is this. The second term, which is this first order PDE, but with this attached to it, which is evaluated over all of the boundary. So if you remember, we had a kidney which looked like this. We had, let me recall, I guess we could go back to it. SA. We had a part of the boundary which we called SA, where heads were defined, and a part of the boundary SB, where fluxes were defined. And so you'll note that this integral is over the entire boundary of the system, not just a portion of it. And this term here is the one that in this second equation has gone here. Because we had, so here, we do the same for y, and we end up with this part here for the first part, which would be this, and we have the second part which goes here. And the rest of the expression that we had from this previous one is exactly the same. We still have flow rate, we still have capacitance, and we have this term here, which is done over the boundary where flux is prescribed. And if I just zoom down to here, so we still have this term here, we have the capacitance term, and we still have this whole thing before that was our boundary condition, which was our flux. So, yeah. Don't get mired in the weeds. Think of the big picture. Let's go back. We've taken this expression. This is our governing equation. We've multiplied it by some number. This is our boundary where flux is applied. We've multiplied it by some number. Together they individually equal 0. Together they equal 0 when they're added together. When they're multiplied by some number, they're still equal to 0. And when they're integrated over the whole system, summed up everywhere, they're still equal to 0. We want to change this part from a second order PDE into a first order by using this identity. And if we do that, then we end up with this expression. That's all we've done. Yeah, go ahead.
The integrals that we're doing, they're both line integrals along the perimeter.
Which ones?
Integral A and integral
A is over the area.
So,
There you go. Yeah. A is over this. So A, the first one for the governing equation is over this entire area that's included in here. So the geometry is that there's this area, and so if we integrate something over the area, it would be dx dy, right? And if we integrate something over the boundary, it would be an integral over the surface B, which would be, I guess, ds, right?
So then SB goes all the way around. It's the entire perimeter.
SB is the part over which the flux is prescribed, which is this lower part. Oh, I guess I can do this. Look at this, blue. This is SB, which is the part over which this flux is prescribed. And SA is the part over which the head is prescribed. Okay? And so I guess on this would be this would be the green part at the top, this would be the blue part at the bottom. I've just found a new toy. I never used to be able to change colors. And the area would be magenta or whatever this color is, right? This area here, right? Okay. So when we write these equations, the governing equation is true everywhere within the area. The boundary conditions are true only on the boundary. This is true on SA, and this is SB. Okay? Okay. So that's key, I think, actually. It's an important point to realize. All right. So, but again, I say don't lose view of the big picture. So what we have is this integral, and if you look at this is the part that we get from this manipulation that we've just done. It's this S is over the whole outside, which is made up of SA and SB, and I guess S is equal to SA plus SB. Because this term is derived from the part of this integral that was the governing equation, it's now over the whole surface contour, SA plus SB. But the previous one where we wrote the boundary condition for was written only over the part where the flux was defined. There's a negative sign on this, so if you take away the part of this integral which was defined only on a portion of the boundary from the integral which was defined on the full boundary, then you end up with the part which is really written over SA, right? So by the same token, I guess you could write S minus SB is equal to SA, just from rearranging this expression here. And you could think about writing integrals for that as well, which would be fine, but not necessary. And so when we subtract this amount here from this, then we're left with this equation here, down at the bottom. I won't write it out. But if you subtract SB from S, you end up with SA. And that's exactly what this expression is here. Everything else has disappeared. All the surface integral parts have disappeared. And so you're left with this term here. You actually have an extra term as well, because within this integral here, you don't originally have this expression here. And so this is one part that's left over from that. This is the term, the integral over SA, which is just left from subtracting SB from SA. And yeah, the remainders are left here as well. Okay. So, as I say, don't get too hung up on this. It's a big picture. So the big part, the big picture that's left here is that now we have a term which represents, if you like, flow in minus flow out. It's written kind of as a discrete form. It's a little bit different from the one we had before. We have a partial with respect to H, but now a partial that relates to this mysterious weighting factor that we really didn't define before, that we've applied to everything. This is W is applied to everything. So this is actually going to be our K matrix. This is our flux that's defined. Flux over the area. This is what we called our capacitance term. And this is our boundary flux. And this is our prescribed flux. So in the same way that this was our K, then these terms will be our H underscore. Remember, our ultimate goal is to get Q equals KH. So importantly, this is the conductance matrix in here. The terms that it operates on are the heads, and the fluxes which are defined at the boundaries are going to be this term here. So this will be Q underscore, and that's all we care about for now. We're not going to worry about how we get flow into the system. We're not going to worry about the time-dependent term, which is our capacitance term. And as it turns out, this is the flux term, which is defined on the part of the boundary, which is where head is prescribed. And so the reality is that this portion is actually going to be satisfied automatically as an automatically satisfied boundary condition. And it's satisfied because if, by definition, we apply on the portion of the boundary where we want to apply the head, and the gradients of head satisfy the governing equations, then the gradients that will be present here will satisfy the head boundary conditions that we apply here. So this part is ultimately going to be automatically satisfied. So we'll deal with that. So if we think about the two main parts of this expression are this, which is the conductance equation for our purposes, and this is our flux part, which comprise our system of equations, then what we might spend some time doing is figuring out exactly what a physical explanation is of this weighting parameters. And the rationale was that we could say governing equation is this. It's equal to 0 everywhere within the system. And so if we satisfy that and we multiply it by any number, it will still equal 0. And if we calculate it at multiple points and add those terms together, they're still equal 0. The weighting functions that we'll apply in a physical sense will look like this. And maybe this is a bit confused. Well, no, it's not confusing. So this is supposed to be one element. Imagine that we divide our system into a series of elements, and instead of being triangular elements, we make them these quadrilateral prisms. What we could do is, and the numbers, these node numbers, as we go around the prism or the rectangle, these are just the node numbers that we apply to it. What we could do is we could make a weighting magnitude, which was some number which we'll call W, and you could think of it just as a spike, a number being given by the height of that point above, the height of that line above a point. So this would be the magnitude of this weighting factor at this particular point, which happens to be a node. And really that's what we've done within our system. So what we could also do is we could say that this weighting factor, we want it to be able to taper away so that as it goes through these other nodes, that the surface that weighting function prescribes goes to be so that it's 0, like a tent, goes to be 0 at each of the nodes in question. This is 4 at the back, right? So this is the weighting function. So that's, I think, what I'm trying to show here. So what I've drawn up here is really this. Nodes 1, 2, 3, and 4 has a weighting function of some magnitude at the node in question, and it tapers off as it goes across the element. And this would what we might call weighting function number 1, because it applies to node number 1. If we go around to the next node and think about what the weighting function would that we apply here, then it's this one here. It's a height of magnitude at node number 2, and this perspective drawing tapers off to 0 at each of the other nodes around here. And this would be B2 or W2 if we wanted to. If we do it for node number 3, this is now the height of this weighting function at the third node, and it tapers off. So the magnitudes that we multiply these equations by is just given by a choice of a number that we choose to map across the element in some way. It equals some number at some specific point. At another point, it would equal some other number, but we don't need to worry about that too much for now. And so if we draw that at an individual point instead of on an element, so what we've done here is we've taken a single element and we've drawn that element out, and we've said that this weighting function could be 1 here, and it would die off, taper off to all these magnitudes here. It could equal 1 here, and it would taper off to the other places. That's one way of thinking about it, because we try and localize things into this single, rectangular element as we go through here. The other way to think about it would be, instead of on an element-centric basis, to think about it on a node-centric basis. And so now we think about it at a particular node on our grid. We have an element around that nodal point here, which is just one of 4 elements that surround this point. And the weighting function at that point would be some magnitude, which we'd call W1 again. But as we went from element to element, if we looked at the other 4 elements that make up that system, then the weighting function that we have here is due to all of those elements that are gathered at that point. And so that's a more convenient way for us. That's the reality of what we're doing when we're applying this weight, because what we've done is we've taken this governing equation, we've given it a number that we've multiplied that governing equation by. We haven't said what that number is, and we've prescribed it here, and we can change that number anywhere within our area A. So all of these elements would be making this overall area A, and the boundary around them, I guess, would be SA and SB. You know, this contour here that I've just drawn along this line, if we thought of our Archidian plan view. And so what we do is we use these weighting functions to be able to prescribe the amount by which we multiply this relationship. And so you could imagine if you take a single element, which I'm bringing up on the bottom, which has nodes 1, 2, 3, and 4, then what we're going to define is that we could calculate what the head is at any place within this element, and we want to be able to calculate it as a function of some functions. And it's going to be some function multiplied by the head at node 1. Some function times the head at node 2, head at node 3, and head at node 4. And so we don't really know what these values of B2 and B1 are yet. But we're just going to arrange it so that we can get the head at any particular point within the element, in this case this point here, as a function of the heads defined at each of the nodal points. And if we write this in shorthand, we can write it as 2 matrix equations. A shape function equation multiplied by a nodal value of heads, which is the same as writing it as equal to BI, BIHI. And summed I equals 1 to 4 in this particular case. So these expressions are the same. This happens to be the matrix form of it. This happens to be the summation form of it. And this happens to be how it would be written longhand. So what's going to happen is that these parameters for B1 and B2, etc., are going to be really what we've referred to so far as these weighting functions. I guess we call them omega rather than 1, but you see the same things. And we can choose these parameters W to be anything we like, and we're going to choose them so they look a bit like this, that they're mapped in some way. Okay? And so if that's the case, then we can write the heads at a particular point as a function of the nodal values, which only exist at the nodes. They don't exist anywhere else other than these particular nodes, these nodal values. And we can map them using these so-called weighting functions. And we can do it for the fluxes, and we can do it for the nodal fluxes as well. And what this so-called Galerkin method says, after the Russian mathematician who devised it, was that we're going to choose these values for these weighting functions that we've kind of defined here. They'll be the same. So the functions that we've defined here will just be synonymous with each other. And so what we can do is we could take these expressions here, and if we roll back 2 pages, we can substitute for, let me do it in blue, we can substitute for this. You should be able to substitute for this and this. And we should be able to substitute for this. And so what now is going to happen is that if these values are, that for instance Q is equal to BQI, not a very, so these would be the fluxes at the nodes, these would be the shape functions, and this would be the flux at any particular point that you want to define. And so what we're going to do is, if we substitute these expressions into this now manipulated differential equation that's integrated, then we end up with a very long system of equations, which is this, just to give you reference of where we were before. Oops, oh, didn't want to do that. Do this. For some reason I like red. Didn't want to do that either. And so once we've made those substitutions, these are the shape functions that end up there. These are the magnitudes of the heads, which are defined at the nodes. This is an integral. This is our conductance matrix here. This is our flux term Q. And the other thing that we can do, even though this is an integration, is that because these nodal values of head are just defined at a point, so they're just defined individually at these points, then the integration of those is null. They don't change as you go throughout the element. And so if that's the case, if these don't change as you change location, then you can take this outside the equation and put it outside the integral. And so if we do that manipulation, and I don't want to go through it, we end up in short form with this very final equation, equation 11, which is the only one that matters. And it gives us a, if I can do my curly brackets, this is the conductance matrix, K. This is H. This is what we will refer to as a storage matrix, S. No, sorry, that's not true. Ignore that statement. This will give us a storage matrix here, which we'll call S, underlined, multiplied in our shorthand for, we've used this shorthand already, H dot. Remember that H dot is equal the rate of change of head. It can be for a single scalar value, or it can be a vector in this case. And so this is the time derivative of head, which is this. And this is our matrix, which we've referred to as Q. And so, although we don't need it right now, we can write out our governing flow equation for groundwater flow, and it looks like this. KH plus S H dot. So this is right. This is KH. This is SH dot. is equal to Q. And so intrinsic from this, we know that the K matrix looks like this, which is what our endpoint was that we wanted to get to when we're there. We know that always our storage matrix, even though we haven't needed to use it yet, will look like this. And if we want to look at steady state problems where this term is 0, then we just have an expression KH equals Q, which we can solve. That's it. And so we could surmise, if we roll this back, that the individual components that make this up are things like, so what are these terms? So the terms that make up this matrix here are terms that look like this. So these are what we refer to as the derivatives of these shape functions. In other words, they're just the derivatives of these tens that we call these weighting functions. And the second component is that the other part, our conductance matrix, which is Darcy's law, is what makes up these individual components here. And so I think it's written, yeah, it is written down below here. So everything that you need really is on this page. Everything that's important, bless you, fits on this. And that is that the A matrix that we have here is equal to the derivatives of these shape functions. And we said before that the shape functions were things that allowed us to calculate head at a particular point as a function of nodal heads and the shape functions, which we have to define. So in other words, by definition, if we figure out what exactly these values for these shape functions are, B, shape functions, sometimes referred to as mapping functions, because that's what they do. So if we know exactly what those behaviors are, then we can figure out exactly what the A matrix is, because it's just the derivatives of those. If we know what Darcy's law is, well, we know that that is exactly that flow rates are going to be equal to hydraulic conductivity times dH dx. This is just shorthand. Comma is the solid mechanics shorthand for partial derivative. And so in 2 dimensions, Darcy's law in 2 dimensions would be flow in the x direction, flow in the y direction, would be equal to a matrix of permeabilities, x, y, y, x, which would be the same as each other, and ky, multiplied by gradients of head dH dx and dH dy. So this is just Darcy's law written in 2D, standard way. In 3D it would be a 3 by 3 matrix. So this is Darcy's law. This is what we've referred to here as our D matrix. Our D matrices are always going to be constitutive equations. So kind of zoom back out. We said we're going to solve problems in solid mechanics and flow. So the D matrix are constitutive equations. It would be Darcy's law in this particular case. This would have units of length over time, hydraulic conductivity. For contaminant transport problems, it would be Fick's law. This would be diffusion, linking mass fluxes to gradients of concentration. And for Hooke's law, for solid mechanics problems, it's slightly different, but this would be displacement gradients, strains, du dx, forces, and this would be modulus, Young's modulus. So, okay? All right. I don't know whether, let's not do this part now, but maybe come back to this. So, accept the fact, I think, that we want to be able to solve this equation. and we know how to do it from what we did last time, except the fact that if we can put together this conductance equation from this, then we can do that. And if we know what the individual components of this conductance equation are in terms of the A matrix and the D matrix, then we can do that. And so that's all that we have to carry forward with us. So there's an obligatory, of course, one-dimensional example. So hopefully, if this seems all very esoteric and to not make much sense, then this hopefully will cement it. We want to solve Q equals KH. If we want to solve that, we need to know what this is, and we do know what this is. We could solve exactly the same problem we solved last time for the dam with two parts. We want to be able to, if we solve the dam in two parts, we need to be able to define what one template looks like in one dimension, and it's going to look exactly the same as we had last time. It has a hydraulic conductivity in the element, it has a cross-sectional area of flow at the ends, and it has a head which is defined at the nodes, and a flux which is defined at the nodes. So nothing so far is any different from last time. Has a length, has a cross-sectional area, has a conductance. We want to be able to make this conductance matrix, which we did just by inspection last time, but this time we're going to do it in a more rigorous way because we now have this fancy equation to be able to do it. And so what do we need to be able to do it? We said that the fluxes are related to gradients of head by Darcy's law. So by definition, D has to be equal to K. So D is just a 1-by-1 matrix. This is our D matrix that lives here. Because we only have flow in the x direction along the element here, we only have one component. And we need to figure out exactly what this A matrix was. And so the A matrix, if we write it out, is exactly this. It's the derivative of the derivative, dH dx, is equal to A times H. These are the nodal values of heads. We know that as we look at this element here, we know that the individual components of this expression here are going to look like Q1 and Q2. And they're going to be linked to values of heads H1, and H2. And if we want to link two vectors together by this K matrix, we know that because this is 2 and this is 2, it's going to have 4 terms. And we actually know what those terms are because we talked about them last time. But in this particular case, the values of heads that we have would be exactly this. And so what we'd like to do is figure out exactly what this matrix is that gives us the gradients of heads as a function of the nodal values of heads, which look like this. So the easiest way for us to do that is just to assume that as you go along this element from node number 1, I'm going to make it a bit bigger maybe, because I can. As you go from upstream to downstream, actually it'd be the opposite in this case, that the head changes from H1 at this place that's at node 1 to this value of H2 that's present at node 2. The only way that we can define a relationship between those is a straight line, and the equation of that straight line is this, right? You can check it out that this is true. So the head at any particular location is equal to the nodal value here plus the difference between the nodal values multiplied by wherever you are on this location. You can easily prove to yourself it's true, because if you choose this point here where x is equal to 0, then the head at this point, h, should equal h1. So if x is equal to 0, this term drops out, h is equal to h1. If you choose this point here, where x is equal to L, by definition, the head should be h2. And if you put x equal to L in here, this is 1, minus 1 plus 1 is 0, and the only term that's left is h2. And the rest of this equation is just the equation of a straight line that maps it between these 2 points. And so this is one way that represents the head difference as we go from node 1 to node 2. And so what we could do is we could take the derivative of this line with respect to x. So if we take dx of h, this term here, it's going to be equal to the derivative of this with respect to x, which is 0, plus the derivative of this with respect to x, which is 1 over L, multiplied by h2 minus h1. And so, by definition, this term here is this. And if this term is linked to the nodal values of heads through this, we could actually write this out in a vector form as, what would it be? It would be equal to 1 over L multiplied by some vector multiplied by h1, h2. And so we need some components of this two-part vector that give us this expression. And clearly we got 1 minus 1 over L outside, so this is going to be plus h2 minus h1. So if you put a minus 1 here and a plus 1 here, then de facto this plus 1 times this gives us this, and this minus 1 times this gives us this. So we've got it. And so heuristically, if you like, we've kind of showed, hopefully to ourselves, that we can get the derivative of heads across here. Of course, in a physical sense, the derivative is constant, right? It's a straight line, so the gradient is constant, and therefore this derivative is a single number. Nodal values subtracted from each other is a single number. The length of the elements is a single number. And so this is just exactly that expression. So this, by definition, I suppose, just to complete it, this is A. And it's the de facto expression that we need. So maybe zoom out again. Literally, we want to be able to get the conductance matrix. We know the constitutive matrix. Now we know what this is as well, as a function of the template. It's just a matrix which is 1 over L minus 1 plus 1. And so if we have both of these expressions, both for A and D, we can put this together. And so let's do that. I don't think I can keep them open at the same time, but this is it. This is just assembling it. And so this is what we want. This is what our element looks like. If we wanted to, and I can draw this out in this way, this would be x. So this would be dx, dy, and dz. And so by definition, if you look at the integral, well, I need some space. If you look at the integral dx, dy, dz, is exactly the same as the integral a times dx, right? Where this here is equal to A. This is x. So in other words, if you think of a little differential element, which is this, if you do the integral dy and dz, that gives you immediately A. And the remainder, so dy, these two terms here would be A, which sit on this face here. And the only variable we have is along the length of the element. And so we can take this expression here, and we can change this dx, dy, dz over the volume into just dx because we've taken the other parts into this. That makes it a one-dimensional integration. We want to know what the individual components are. We said D is equal to this. We said that the A matrix is equal to this. You can do this. This is just the same calculation we did on the previous page, but this is the A matrix. And so what we can then do is we can assemble this matrix from these components. We have D, we have A, and this is just it. So this is, we've taken A outside. This is the integral A transpose d A dx now, right? The difference between x and v is just what we did above. And so now this is the area. Are we supposed to be finishing? People are very prompt, 10 minutes early. The A matrix, which is this, is here. The D matrix, which is here, is here. And the transpose of the A matrix, which is just flipped, is this term here. So those are the three terms that go into that. Just so you can see it. And the constants can go out. So if you gather the constants, we have a constant. Let me change color here just because I can. So the constants are A and over L and over L and K. So A, L squared, and K were all taken out. And then if you do that, the only remaining terms that we have are the two vectors, which exist here, which are multiplied by each other. And if you know your laws of vector multiplication, it's going to be a 2 by 2 matrix. -1 times -1 gives you +1. 1 times -1 gives you -1. -1 times +1 gives you -1. And +1 times +1 gives you +1. So I'm just going to erase those. So this is the matrix. And just like anything, even though it's still inside an integral, the integral means that you take each of these components of the matrix and you integrate them. So this term here would be just, bless you, A k over L squared, integral of 1 times dx. And it's integrated between limits, which is the same as AK over L squared times this integral. The integral of 1 with respect to x is just x. And it's evaluated between the endpoints of the element, the x coordinates of the element x. So x1 is the x coordinate of node 1. Actually, I can draw it just as easily. So this is our element. This is our x coordinate here. This would be x1 and x2. And so if we multiply those out, x1 would be 0 if we take our origin here. This is the length of the element, which is of length L. So if this is 0 and this is L, then the integral from 0 to L of x is just going to be equal to L. So in other words, this term here is just going to be L. L divided by L squared gives you AK over L, which is this term here. And if we go back to this, then this is just the template. That's just the integral. And so, not surprisingly perhaps, the conductance matrix that we have is exactly the same as we had when we did this one-dimensional problem last week, on Thursday, which is the area of the element, the hydraulic conductivity in the element, the length of the element, and just 1 minus 1 minus 1, 1. And we could use it in exactly the same way as we used last time. So it's not surprising that we ended up with the same outcome. In fact, we'd be surprised, I think, if we didn't end up with the same outcome, because the element is exactly the same as we had last time. It looks exactly the same and is described in terms of the same parameters. But what it allows us to do now, I guess the step forward that we have is that now we know that we can always get our system equations which look like this. And we always know, for any problem we want to solve, we always know exactly what our K matrix is going to look like. It's going to look like this. And it's important for two reasons. One, because now we're no longer limited to one dimensions, which is what we had done last time. We can do two-dimensional problems and three-dimensional problems. And the other thing is that we can also use elements which are much more sophisticated. And so, for instance, in this particular case, we've chosen an element that looks like this brick. And by definition, along the length of it, if we plotted head versus location, then by definition, it looks something like H2 and H1. And it's been a linear distribution between those. What we could do is, if we wanted to, we could put an intermediate element or node in this element, in which case we could perhaps define behavior along the element, which instead of being a straight line, which by definition we need to do to be able to solve this problem, is it could actually be a quadratic distribution. So in other words, instead of being this straight green line, which is this linear relationship which implicitly we chose because we did this, we chose it to be linear because that's all we could justify that would go between these 2 points and was defined by those 2 points. If we had an intermediate point partway through, we could write a system of equations which now has an intermediate node in the element. And so we can do two things now with this newfound capability with this conductance matrix. One, we can do two-dimensional problems and three-dimensional problems, and they follow on logically from everything we've done. The indexing that we did to solve this calculation example last time and get the fluxes and the heads, we can do exactly the same the next time. And we can also deal not only with multiple dimensional problems, we can also deal with much more sophisticated elements, which this opens up the door to. So I would say if you don't feel comfortable with the stuff that we've done today early on, don't worry about it. It's absolutely of no consequence. The only important part is to get to this page here where we end up with these expressions. I don't know if you'll have a chance to do with it. This one page is worthwhile looking at because you'll see all the steps that we went through on this kind of long-winded thing in a much more condensed fashion, and you might be able to rationalize exactly why things end up the way they do. And you'll see here at this endpoint, this is just our governing equation, and you can see it comprises a conductance matrix. This should actually be equal to Q, right? But it's a conductance matrix applied on a pressure instead of a head, and a storage matrix applied on a rate of change of pressure. Old main tells me it's time to finish. Right on the number. Okay, so have a look at that.